Hi, welcome back to this course on differentiable manifolds. Here is a very short video to convince you that any Lie group is parallelizable. What did I say? Parallelizable? What does it mean? Hold on. Let me share with you the following. So the title is any Lie group is parallelizable. What does parallelizable mean? Given definition. A manifold M is parallelizable if the tangent space to M decomposes as a product. So it's really here, this means diffeomorphic. It's diffeomorphic to the product of M with the tangent space at a certain point. Okay, that's a very strong statement because, of course, the tangent bundle is a bundle, so it might be not trivial. So let's see what happens when we have a Lie group. So let me make a picture of a Lie group. I'm going to make a picture of a Lie group. So let G be a Lie group let's make the picture of the Lie group as such. So that's G, okay? And now I consider the identity element here. I have an identity element because G is a Lie group, therefore in particular it's a group with a smooth structure such that the product and the inverse are smooth manifolds. So I'm going to introduce for you a very important transformation, which is a diffeomorphism, which is defined in the following way. I consider the following diffeomorphism for any element G on the Lie group. Okay, I consider the mapping that goes from G to G that sends L. So let me arrange this. I consider here so for any element G, on the group. Okay, I fix the G on the group, and then for any H, I send H to the product of G times H, where this is the product on the group. This transformation, of course, is a smooth because it's defined as the product of two elements of the Lie group, and by definition of a Lie group, this is smooth mapping. Observe that, so the remarks that are in order now. LG is a smooth, and LG has a smooth inverse. Which is multiplied by G minus 1, which of course is a smooth, as the product and the inverse are smooth on a Lie group. Okay. In particular, this implies that L sub G is a diffeomorphism. And that's a powerful statement, because whenever I have now, I'm going to draw again my Lie group. Well, I draw this Lie group as a sphere, but it cannot be S2. You'll see why in a minute, precisely. Let's imagine that this is indeed S3, which is a Lie group. Okay. And now, and indeed, it's the Lie group determined by unit octonions. So I'd like to put it like this. I'd like to first, it's not too big, it's too gross, this sphere. Let me redo it. So I'm going to do this sphere for you. That's S3, which can be identified as the set of unit quaternions. And because the set of quaternions is itself a group, S3 inherits from the group structure of the quaternions a group structure itself. Of course, well, this group structure becomes polynomial when we look at it in coordinates, and of course, this group structure, it's smooth, and then S3 is a Lie group. Now, on this Lie group, I take S3 as example, right? I take a point, and I'm going to take this point to be the unit, which I'm going to make a picture in, maybe in red. So here I take the unit element, okay? And therefore I know that if I take another element of the group, G, I can always go from E to G by multiplying by left transformation. And I can do this on S3, or I can do this on any group. This works on any group. In particular, an interesting thing I can do, now imagine that I have any group, this transformation, what it does an interesting thing. First, it connects to any given point on the group, okay? If the group is connected, it connects, then these two are in the connected component of the identity. If it's not connected, then it connects any two elements this way. And the second thing that we can realize very, very easily is that if I take the tangent space at a given point, I'm going to put the tangent space in pink at the identity, take the tangent space at the identity of the Lie group. This has a big name. This is the Lie algebra. Okay, we know this is a vector space with a particular Lie algebra structure. And then if I take a vector here, the differential, and I take the differential of the left translation, it's going to take the tangent space at a given point E to the tangent space at a given point G. Okay, so if I take this is going to transport this tangent space to the tangent space at each point. Therefore, in particular, if I have a vector such that it's I take a vector here, then it gives me a vector here. Of course, because LG is a diffeomorphism, this is an isomorphism at any given point. In particular, E, it's an isomorphism. So it cannot do strange things. If I take a vector field that doesn't vanish, if I take a vector, of course, non-vanishing is going to be a vector. It takes it, it transports it to a non-vanishing vector, but it does more for me, okay? What it does for me is that now if I take a basis, we can take a basis, okay? This gets transformed into a basis. So, because it's an isomorphism, sense basis to basis. This is very clear. Okay, so now in particular, with this very simple remark, what we are proving is that the tangent space at any point, you can get there from the tangent space so that you have that the tangent space at any point, you can get it from the tangent space at the origin, just using the differential of the Lie group G. So what I'm saying is that this is isomorphic to the group itself, okay, times the tangent space to the identity. And how this isomorphism works? Well, this isomorphism works in the following way. We have constructed it already. We take a vector here times an element of the group, okay, and we send this, okay, to the point G, and the differential of L sub G at E of B, which lives on the tangent space at G of G, okay? And we can check that this transformation is smooth and defines an isomorphism. So the consequence, and that's the big consequence that we obtain, any Lie group is parallelizable. So the tangent bundle of G is isomorphic or diffeomorphic indeed to the group times the tangent space at the identity. And this is of course G times G. Okay, so so that's an important consequence. So let's look at some important corollaries of this indeed theorem. And so corollaries. First corollary, and that's an interesting corollary, S2 cannot be a Lie group. Why is so? Well, remember that we have the Haley-Wald theorem. It's telling me that any vector on S2 has a vanishing point for any vector. So let me write this properly. There exists at least a point P, and vector field, and this vector field I'm going to call it X, such that x of P equal to 0. Remember, the Hairy-Ball theorem can be maybe what you recall from the Hairy-Ball theorem is the picture of it, right? The picture of it is that you have the sphere, that's really the sphere, and then you cannot come a sphere. That's why it's called a Hairy-Ball. So there has to be a point where you cannot really come the sphere, a point where you cannot come the sphere, and this implies that here the vector field has to vanish. Okay, so that's an important consequence. So that leads me to the following observation, or the following question. Which spheres admit a Lie group structure? And the answer well, let's go and try. First, as 1. Let's start with n equal to 1. Well, I could consider also as 0. These are 2 points, and I could think that this is a discrete group of 2 points, that this is like set 2, therefore it's a Lie group. But let's start with S1. S1 lies inside the complex numbers with the complex multiplication, and I can identify this again with the complex numbers of norm 1. Okay, this is a subgroup that indeed, in particular, S1 is a Lie group. Okay, and well, let's go on. Let's look at S2. S2 is inside R3, but we have argued that this does not admit, it's a fail, it does not admit any Lie group structure. What else? Let's go to S3 and let's say what happens. So we have, so far, we have a fail, we have an okay to go and a fail. Let's see what happens with S3. I already announced this before. I may consider S3 as the set of unit quaternions. So S3 is the set of points on Q with on the quaternion such that the ROM is equal to 1. This makes S3 into a group. One can check that this group is induced a smooth structure, therefore S3 is a Lie group. What else? So I have another yes here. Great. What happens with surfaces? Well, which surfaces can admit a Lie group structure? Well, first of all, we know they have to be orientable. This excludes quite a lot. And second, they have to be parallelizable. Therefore, the Euler characteristic of this surface, which is 2 minus 2g, has to vanish. And this leaves me with the case of genus 1. And I know what is the case of genus 1. It's my favorite donut. So the case of genus 1 is the case of the torus. The torus, we already know it has a Lie group structure. It's the product structure of S1 times S1. Okay, and with this, I finished the class of today. I hope you enjoyed this class. And well, now we know something else, something new. See you soon.